Ralph H. Miller significantly contributed to internal combustion engine technology by developing the Miller cycle, a variation of Atkinson cycle that improves thermal efficiency by controlling intake valve timing. His invention, patented in 1957, involved reducing the effective compression ratio by adjusting the intake valve closing timing, allowing for a higher expansion ratio and consequently higher efficiency.
Introduction to Miller cycle. The Miller cycle is an advanced thermodynamic cycle used in internal combustion engines that modifies the conventional Otto cycle. To improve efficiency, it features a unique combination of the intake valve timing and compression radius, which allows for a longer expansion pace than the compression pace of Miller cycle. Delayed intake valve closure. In the Miller cycle, the intake valve closure later in the compression stroke, allowing some of the air-fuel mixture to escape. This leads to a lower effective compression ratio while maintaining a higher expansion ratio. So explanation and delayed intake valve closure in Miller cycle is to intake the valve remain open longer during the initial parts of the compression stroke. This results in a portion of the intake charge being pushed back into the intake manifold, effectively reduce the amount of air-fuel mixture by compressing. So in increasing efficiency, the longer expansion pace allows for more energy to be extracted from the combustion process, resulting in improved thermal efficiency. So in simple explanation about increased efficiency in Miller. So this lower compression losses in cylinder temperature, resulting in less heat loss and reduced knocking. Combined with any longer expansion stroke, more energy and extracted from the combustion process, leading to improved thermal efficiency and better fuel economy. And reduced pumping losses by allowing the intake valve to remain open longer than engine experiences reduced pumping losses, which contribute to better overall efficiency. So what is reduced pumping losses in Miller? So in Miller cycle, the delayed intake valve closure reduces the amount of the air drawn into the cylinder during the intake stroke. This effectively lowers the vacuum in the intake manifold, which reduces the resistance the engine faces with drawing in the air with the pumping losses. So in application, commonly used in modern gasoline engine and some diesel engine, particularly in the application where efficiency and emission are critical. So about an application of the Miller cycle. So this cycle is found in some hybrid vehicles, which performance engines in large commercial vehicles. Its ability to improve thermal efficiency and reduce knocking make it ideal for application that requires both powers and fuel efficiency, such as automotive engine and aircraft.
The Miller cycle is a thermodynamic cycle used primarily in internal combustion engines to improve efficiency and reduce emissions, and it consists of 5 sequential processes. First, an adiabatic compression from state 1 to 2, during which the working fluid is compressed without any heat exchange, causing its pressure and temperature to rise while its entropy remains constant. Second, an isochloric constant volume heat addition from state 2 to 3, where heat is added to the compressed fluid at a constant volume, leading to a sharp increase in pressure and temperature. Third, an adiabatic expansion from state 3 to 4, where the fluid expands without heat transfer, doing work on the surroundings while its pressure and temperature decrease and entropy remains unchanged. Fourth, an isochoric heat rejection from state 4 to 5, during which heat is removed from the fluid at a constant volume, resulting in a significant temperature and pressure drop. And finally, isobaric constant pressure heat rejection from state 5 back to 1, where the fluid continues to reject heat at a constant pressure, completing the cycle and preparing the system for the next round, with the overall process being represented graphically in the PV and TS diagrams, where each segment corresponds to one of the described processes, and the combination of these steps allows the Miller cycle to achieve better thermal efficiency and lower combustion temperatures compared to the traditional Otto or diesel cycles by utilizing techniques such as delayed intake valve closing or supercharging.
So process 1 and 2, isentropic compression process. So this is the formula of isentropic compression process. First is the T2, or the temperature 2 over 1 equals to pressure 2 over P1 raised to K1 over K equals to V1 over V2 raised to K minus 1 and 1 over K minus 1. So the next is the T2 over T1. So the T2 over T1 raised to 1 over K1 equals to P2 over P1 raised to 1 over K equals to 1 over IV volume 1 over volume 2 equals to isentropic compression ratio or RK. RK or isentropic compression ratio equals to V1 over V2 equals V2 plus VD or volume displacement over V2 equals CVD plus VD over CVD. RK equals C plus 1 over C. So process 2 and 3 constant volume heat addition process V equals C. So the formula is T3 over T2 and equals to P3 over P2.
Thermodynamic process and equation. The equation describe the relationship between temperature, pressure, and volume during various thermodynamic process. Specific, they relate the isochoric expansion and compression, isochoric heat rejection, and isochoric heat rejection. During isochoric processes, the entropy remains constant, and the relationship between temperature, pressure, and volume are governed by specific equation. The isochoric expansion ratio denoted by R is critical parameter in this process. In contrast, isochoric heat rejection occurs at constant volume, while isochoric heat rejection occurs at constant pressure. These processes are essential components of various thermodynamic cycles, including the Otto cycle. Understanding these thermodynamic process and equations is crucial for analyzing and optimizing the performance of internal combustion engines and other thermodynamic systems. By applying these principles, engineers can design more specific and effective systems.
So heat rejection process is constant pressure equals to pressure volume over temperature, and heat addition process or heat added equals to mass constant volume absolute temperature. For heat rejection process, or you may call QR, constant volume heat equals to mass constant volume absolute temperature.
Heat rejection process 5 to 1 where pressure is constant. So the formula heat rejected is equal to negative mass times specific heat at constant pressure times temperature 5 minus temperature 1, and next is work net. So the formula work net is equal to heat added minus heat rejected in process 4 to 5 plus heat rejected in process 5 to 1. Efficiency of Miller cycle. So the formula is efficiency of Miller cycle is equal to work net divided by heat added times 100%, or heat added minus heat rejected at process 4 to 5 plus heat rejected in process 5 to 1 divided by heat added times 100%.
We will now solve a sample problem for related to Miller cycle. So I know, guys, that you can see the problem. I will let you read it and familiarize the PV diagram and the TS diagram, and also take note of the given. Since if we know how to use this given correctly, it will shorten, or it will make it easier for us to solve this problem. So the required for this problem are the temperature 4 and the pressure 4, and what we have is only the compression ratio, the expansion ratio, and the pressure 1 and T1, which is not enough. And we also have the QA, which is the heat added, the constant volume, the constant pressure. We also have it. Now let's solve it. Okay, also take note that the K is equals to 1.3 because it is stated that it is a hot air. But if this is not given, we can assume it as directly 1.4. But if it is given, you really must use it. But if it's not, use 1.4. Okay, so now we will start solving the problem. So before starting, I want you to look at your upper left, where you see this T2 over T1, 1 over K minus raised to 1 over K minus 1 equals to pressure 2 over pressure 1 raised to 1 over K equals volume 1 over volume 2 equals to compression ratio. Again, we have our compression ratio. This formula means that you can use the two to equate and then solve for the missing part. For example, the volume 2 is missing, the pressure 1 is missing. Now we will use this to solve temperature 2. Again, based on the given, we have the temperature 1 and also the compression ratio. Now we will use the T2 over T1 raised to 1 over K minus 1 and then equate it to the compression ratio to solve the T2. After equating it, then now we will have the temperature 2, which is equal to 599.8 Kelvin. Now for the pressure 2. Since we're solving for pressure, we must use this second formula on your upper left, which is P2 over P1 raised to 1 over K. After solving for T2, you can equate it with the first formula. But since it's harder to do, we will equate it instead with the compression ratio. since the compression ratio is given. But if the compression ratio is not given, we can equate it with the other formula as long as it's there. But if it's not, then this problem is not solvable at all. Now, since we have our compression ratio equated for the formula of the pressure, which is P2 over P1 raised to 1 over K, now we have the pressure 2 as 495.1 kilopascals. Now for point 1. The point 1, here we can solve all of the 1. What I mean is the pressure 1, the volume 1, and the temperature 1. But since we have the pressure 1 and the temperature 1, we will now only solve for the volume 1, which will be using the formula for ideal gas law, which is pressure times volume is equals to mass over RT. And since the R is also given, which is 0.287 kilojoules, now we can just substitute all of it to the problem that solve for the volume 1. Now we have the volume 1 as 0.861 minute cube or meter cube I forgot, over kilogram. Now, since we have the volume 1, again, look at the formula in your upper left. We have the volume 1 over volume 2. We will use that and then equate it to the compression ratio to solve for volume 2. Now we all have the pressure 1, the T1, the T2, the pressure 2, the volume 1, and the volume 2. The 1 and 2, now we are using 3 and 4, since we are solving for the process of 3 to 4. Now, since we have our volume 3, now we can solve for the volume 4. And how to solve this, we use the formula of V4 over V3 and then equate it to our expansion ratio. Since the expansion ratio is given, which is 12, then now we can just substitute all of it to the formula and then solve for V4. After solving for V4, now we have it. And then after solving for V4, we proceed with solving the T3 with the half of the Q added. And always remember that the formula for heat is that Q equals M times the specific heat rate and then times it to delta T. But since this is a Miller cycle and the Miller cycle does have a constant volume, we will be using the constant volume instead for the specific heat, or the which is now we will have the formula of Q added equals mass multiplied to constant volume multiplied to delta T, or the change of temperature. But here in this slide, you can see that the delta T is expanded so that we can solve for T3. And since we have our QA, but the mass is not given, so what we shall do? If the mass is not given, we can just assume it as 1 kilogram and then proceed with solving. But if it is given, we can just substitute it to the formula. But if it's not, we can assume it as 1. After assuming it as 1, we can now proceed with the solution. And then, now we have the T3, which is 1415 Kelvin. Now since we have the T3, now look again at the formula in the center, upper center. See? You see that T3 over T4, 1 raised to 1 over K minus 1. We will be using that to solve for T4 by equating it to our expansion ratio, since the expansion ratio is given. But if it's the case that the expansion ratio is not given, now you can use the volume 4 and the volume 3 or any other given as long as it is there. But since it's not, we should just use the expansion ratio. It will be also easier. After solving for that, substituting all of the given into the formula, now we can solve for T4. As you can see here at the bottom, T4 equals T3 over expansion ratio raised to K minus 1. Or you can just also directly input it as T3 over T4 raised to 1 over K minus 1 equals to expansion ratio, then press shift solve for X. Change T4 with the X in your calculator and the calculator will solve it directly for you. Now the value of our T4 is 671.4 Kelvin. Now what we are lacking is the pressure 3, pressure 4, and those are the pressure 4 and pressure 3. Since we have the T4 already, we are only one down to go. So for solving for P3, again we will use the ideal gas law. Actually, you can use the ideal gas law as long as the sub 3 of the volume and the temperature is given. But since we already have it, we can now solve for P3. Now, as you can see here in the center, he derived the formula of P3 to R equals to R T sub 3 over volume 3. After deriving the formula, solve for P3, he go back to using the formula of this. You see these 4 solutions in the center. I'm solving for P4 from this one. Now, since we're solving for pressure, we will focus on the pressure 3 over pressure 4 raised to 1 over K, and then equate it to our expansion ratio to solve for P4. then substitute all of it. Now you will have your answer, which is 21.9 kilopascal. Again, you can just input it directly to your calculator and substitute what is missing as x, and then shift solve for x, then the calculator will solve it directly for you. So here we go, we have solved this problem. We already found the pressure for and the temperature for, which is 21.9 kilopascals and 641.4 Kelvin. And I hope that you understand the whole process, as it will help you a lot in the future, especially tomorrow, since tomorrow is our examinations and these are the topics that will pop up.
Basic equations. Efficiency of Miller cycle. The thermal efficiency can be expressed as efficiency of Miller cycle is equals to 1 minus 1 over Rk raised to k minus 1 times 1 divided by Re raised to 1 minus k, where Rk is the compression ratio, Re is the expansion ratio, and K is the heat capacity ratio. So here are the problem solving examples. So example number 1, for the efficiency calculation. Problem: calculate the efficiency of a Miller cycle engine with a compression ratio of 10 and an expansion ratio of 1.5 and a heat capacity ratio of 1.4. Solution: the Miller cycle modifies the effective compression ratio by early or late closing of the intake valve, which affects the expansion ratio. The thermal efficiency can be approximated by adopting the ideal Otto cycle efficiency formula to include the expansion ratio. So, the thermal efficiency for an ideal cycle with differing compression and expansion ratios is efficiency of Miller cycle is equal to 1 minus 1 all over Rk raised to k minus 1 times 1 all over Re raised to 1 minus k. So, this formula accounts for the fact that the expansion ratio can be different from the compression ratio. This formula accounts for the fact that the expansion ratio Re can be different from the compression ratio Rk. So, Rk raised to k minus 1. So, we're going to substitute the values. So, our Rk is 10. So, 10 raised to the value of k, which is 1.4 minus 1. So, is equal to 10 raised to 0.4. Next is for the Re. Re raised to 1 minus k. So, the value of Re is 1.5 raised to 1 minus the value of k, which is 1.4. So, the answer is Re is equals to 1.5 raised to negative 0.4. Then, the value of 10 raised to 0.4 is approximately 2.5119. And the value of 1.5 raised to negative 0.4 is equal to 1 all over 1.5 raised to negative 0.4 or also equal to 0.851. Next, substitute the formula. 1 all over Rk raised to k minus 1 times Re raised to 1 minus k. So 1 divided by the value of Rk, which is 2.5119 times 0.851. So the answer is 0.3387. Next, we're going to compute the efficiency of Miller cycle. So substitute the values. 1 minus 0.3387 is equals to 0.6613 times 100% to calculate the efficiency. So 0.6613 times 100% is equals to the efficiency of the Miller cycle, which is 66.13%.